Okay. Now, the next question is then how to obtain a more detailed definition. And I already mentioned to you that every estimate of probability that satisfies these axioms is acceptable. And of course, now if we want to estimate the probability of an event, we have to provide a method to perform to get this estimate. And therefore, there are several interpretations, they are called interpretations of probability, that were proposed by the literature, where by interpretation I mean a practical method to estimate it. Let me anticipate that there is an interpretation which is called Bayesian, which is just subjective. So you estimate the probability by guess. This is the Bayesian probability. It's also called Bayesian definition of probability. So I mentioned, I used the term interpretation, but in some textbooks you see Bayesian definition. And the Bayesian definition is not opposed to the axiomatic definition. The Bayesian definition respects, or Bayesian interpretation meets the axiomatic definition. And I think it's important that you know this term. What is Bayesian probability, Bayesian approach? And according to the Bayesian interpretation, you define probability subjectively, by guess. And this is extremely useful in some cases. Like, for instance, tossing a coin, by your perception, you can estimate that the probability of getting a tail is 0.5, which is correct. And of course, your perception could be correct. The fact that an estimate is subjective or perceptual doesn't mean that it's wrong. It could be wrong, but it could also be correct if your perception is good. So to estimate probability in a perceptual way is fine. This is one way of defining probability. And also, I mentioned that it's very useful because in some cases, it's the only interpretation that you can use. Let's say, for instance, if you want to estimate the probability of winning the election by a party, you may say the probability of the party to win the election is 0.6. This is a perceptual estimate, and there might be no other way of getting an alternative estimate. Because of course another way could be the telephone pools, etc., to get the opinion of people. But these are relatively recent methods. In the past, when people tried to guess the probability for a party to win the election, they were basing the estimates on the opinion of experts, which means a Bayesian estimation. If a person is very expert, then he can estimate well the probability of a party to win the election. And this could be the only way, as I said, to estimate probability. Bayesian probability has a set of rules. Some of them are very mathematical to support the estimation. It's not just perception, it's some more in some cases. A set of rules that have to be met. So Bayesian probability is well codified. And especially it's well codified how to update the estimate. Because Bayesian probability usually calls the preliminary estimation the prior estimation. They say prior probability, which is maybe very subjective, and then you could get some information. Like for the election, you get a prior probability which is subjective. And then you make a telephone pool. And then, based on the results of the telephone interviews, then you update your estimate, your perceptual estimate, by obtaining the posterior probability. And there are a set of rules that help you to update the preliminary estimate. To update the prior distribution, prior probability to get the posterior. So this is one possibility. There is another possibility. Let's assume that you can make an experiment that consists in generating several outcomes from your event. Let's suppose that you can make an experiment then. So let's suppose that this event is repeatable. An election is not repeatable. But if your event is tossing a coin, this is repeatable. So let's say that you don't know the probability of getting a net from tossing a coin. You could say, let me try. And then the famous statistician Pearson, who operated, I'm not sure, I think he operated around 1700, he made an experiment, but not because he didn't know the result, because he wanted to prove that this is effective. He tossed the coin 24,000 times, and he got 12,000 plus 10 heads. And he wanted to prove that this is a very good estimate of the probability of getting a tail or a head in tossing the coin, if the experiment is tossing the coin. Of course, this is very trivial. You may say, well, why do that? It's clear that the probability is 0.5. Yes, but there are experiments which are not so, whose result is not so evident. Let me make a hydrological example. Let's say that you have a long series of rainfall, daily rainfall, and you want to estimate the probability of rainy days. So basically what you do is to fix a threshold value to classify a day as rainy, and usually it's 1 millimeter of rain. And you count, let's suppose that you have a sample of 10,000 daily observations, you count the number of rainy days. And if the number of rainy days is 2,500, you conclude that you have a probability of 25%, 0.25, to get a rainy day. This estimate of probability basically computes the probability of A as the number of A, and let me say, use this symbology, divided by N, where N is the total number of trials. What is this? This is the relative frequency of the outcome. This is a relative frequency. So basically, this estimate is derived by equating the probability of an event to the frequency, to the relative frequency of that event. And you can easily realize that this estimate satisfies the three axioms. It's very easy to satisfy this. You see that this estimate varies between 0 and 1, of course. So the first and the second axiom are satisfied. And if the event are disjoints, also the third, the additive one, is satisfied. Because think tossing a coin, it's clear that the event are A and B, and the probability of A plus the probability of B estimated in that way is 1. So that's fine. And this is called the frequentist definition or frequentist interpretation of probability. Frequentist probability. If it will happen to you to deal with statistics in your future, you will know about a very important and very strong debate between frequentists and Bayesians. Both of them claim that their method is the best one. And they are really fighting, because of course there are some cases in which you can use just one, you can use just Bayesian probability. But there are many events, many experiments for which you can use both. like tossing a coin. Tossing a coin, they debate why performing the experiment is needed. Bayesians say, why do you need to perform an experiment? It's clear that the probability of getting a red is 0.5 and you can get the estimate by perception. So why should you perform the experiment? Of course, in this case, the debate is trivial. But for instance, there are other cases in which you can use both, and they debate continuously, and they fight, really, because they want to promote one approach or another. And my opinion is very simply that they are both useful, and it depends on what you have to do. If I had to estimate the probability of rainy days and I had a long series, why should I use a Bayesian approach? It's so simple to count the number and use the frequentist definition. But this is just the opinion of a very practical statistician like me and not very informed. But it's good for you to know that there is strong debate. And Bayesians, typically, they are a bit fanatic. Typically. Okay. Now, given this definition, you may say that you know everything now, because let's assume that you can perform this experiment, and if you can perform this experiment, the frequentist definition allows you very easily to estimate the probability of an event. So if we talk just of events like number of rainy days, probability of rainy days, or probability of in hydrology, let me think, what is another example that I made? Probability of getting a river flow which is above a given threshold. This is very simple. You can estimate the probability according to the frequentist definition. The thing becomes a bit more complicated when you deal with random variables which can assume any real number. So this definition needs to be a bit completed, because so far, tossing a coin, the result is not a real number. It's just 0, 1, it's binary. It's head, tail, it's binary. So this random variable, which I used as example, tossing a coin, is binary. Rainy days, same thing, it's binary, yes or no. So it's not a real, the random variable, the associated random variable is a binary one. It's not a real variable. Or exceeding a given flow threshold is binary, 0, 1, 1 if it is exceeded, 0 if it's not exceeded. So it's very easy to define for binary variables, but also for discrete variables. When the number of outcomes is finite, this is a big difference. When the number of outcomes from an experiment is finite, then you can use that definition, and it's very easy. But the problem is that if you speak generally of river flow, the river flow is a random, it's a real number, and the number of possible outcomes is infinite. So if you use that definition for estimating the probability that the river flow is 25.12345 1000 of digits, and you make the experiment, the number of outcomes that meet this number is 0, because of course the real number has an infinite number of digits, so you will never get that outcome. And therefore, you would get, according to this definition, that the probability of getting any assigned value of river flow is 0. So basically, whatever river flow you fix, the probability of getting that number is 0. So this definition needs to be updated. You need another definition. This is fine when the number of outcomes is finite. If the number of outcomes is infinite, like for a real random variable, you need to devise a different definition. And let me say that this step of passing from discrete variables to real variables is, in my explanation, in my today's lecture, probably the most difficult one to understand. So I will try to be very practical. So let's suppose that your outcome from the experiment is given by a real number, like river flow. the most obvious solution is to discretize the real number. So let's suppose that this is Q, river flow, which varies between 0 and, let's say, let's fix an upper value, but it's not necessary. Let's say infinite. Then the most obvious thing is, let's break the range of possible river flows in a finite number of segments. Finite number means that if you want to extend until infinity, you have to take a unique segment between a given value to infinity. So let's say that you are interested in modeling your river flows up to the value of 100, and then you can get a unique segment between 100 and infinity, because you need to make the possible outcome finite. So if you do that, then it's easy. Let me say that it's not strictly necessary that you get just one segment from 100 to infinity. Let's say that you split the possible range of values in segments. That's it. Even if they are infinite, it's not a problem. Then you get your observed river flows, and you count the number of times, and you have an observed river flow. You count the number of times in which your observations fall within each range. So the number of times could be, let's say, 2, and then 3, and then 5, and then 10, and then 30, and then let's go down to 25, 20, 5, 1, and then 0, 0, 0, 0, because after you reach the maximum value of the observed flow, you get 0 for any greater value. And then, you know, it becomes easy to estimate the probability for each of them. And so if you divide by n each of these numbers, you get the probabilities. So you are still using the previous definition. Etc. You are still using the previous definition, and then you could display the probability here. And the problem is that, you know, if you display the probability here, it's a step function, it's not a continuous function. So you start from, let's say, something like this. The graph is not proportional, so be patient for this. Okay, and then you get something like this. Where here the sum of the probability is equal to 1. Sorry, I think it is this one. Let me see. Okay, fine. Okay, this is one possibility. And let me indicate with the symbol delta x the width of each segment. And let's suppose that it's the same width, same width. Okay, yeah?
How did you define n?
And this one? It's simply the number of experiments. If you have a time series of river flows, n is the total number of observations. If you are, the experiment is tossing a coin, you just take the number of times that you want to toss a coin. In this case, given that I refer to river flows and I made it clear that they are observed river flows for which I want to estimate the probability, then it's clear that N clear. Let me say that N, capital N, is the total number of observations. So if you have 10 years of daily river flows, it's about 3,650. 3,650, yeah. Okay, that's fine. And we may say that this solved our problem. And I would say no, this is just a workaround. It didn't solve our problem. Because our problem is to estimate the probability of a river flow, a given river flow. In this case, if you had to assign a river flow value to these probabilities, what would you say? So one possibility could be that you take the center of the interval and say, okay, this is Qi in the center of the interval, but this is an approximation. And it's an approximation. Why? I make it very clear that it's an approximation, because if you said that this probability here is the probability of Qi, if you said that, I would say, look, if you change delta x, it changes your estimate of probability, which is not reasonable. If you say that the probability of Qi is 0.2, it must not depend on the size of the delta x. So it means that what you are estimating is the probability of getting a river flow between Qi and Qi minus delta x over 2 plus delta x over 2. So you are estimating the probability of your river flow to fall into this range, not the probability of Qi. So I would say, no, you didn't solve the problem. You are estimating the probability of the river flow to fall in the range 90, 100, let me say. You are not estimating the probability of 95. So, how to solve the problem? The problem is solved in this way, is solved by providing this estimate by introducing, another definition, and it's the definition of probability density. So let me call with the symbol lowercase p, let me define the ratio between probability of Qi, which I define that, capital P, so let me indicate in this way, divided by delta x. In this way, and let me say that, sorry, I rewrite because I need some space here. And let me compute the limit for delta x tending to 0. Which is possible because this is a real variable. So I could also do that by hand. If I had many, many observations, I could try to decrease delta x and see what is the limiting value that is assumed by this lowercase p for delta x tending to 0. What is this lowercase p? It's called probability density. is independent of delta x, because delta x is tending to 0 and it's independent of that. So what is the probability density basically? It is a measure of the probability that you have to get a river flow that is infinitesimally close to Qi. Yes, what is the probability density? Is the probability that you get, that you estimate to get a river flow that is infinitesimally close to Qi. And then your question could be, but is this helpful for me? Yes, it is, and I'll explain you why. Because, you know, it's not helpful that you ask yourself what is the probability of getting a fixed river flow because it is 0. But it is very helpful for you to know what is the probability of getting a river flow that is sufficiently close to the given value. And I explain you why in just one moment. This step that I'm explaining to you, it's one step that I didn't find so far a more practical way to introduce it. And now I become more practical. In the next step I will be very practical. But indeed, in this, I understand this definition is something that you can't really associate to something really practical. And so, if you have any suggestion for making this step more practical, it would be great. Now, let me now become practical and explain you why it is useful, why the probability density is useful. And in order to prove to you that it's useful, let me compute the integral between 0 and Qi of this probability density defined in this way. So, what I think I can delete here. So basically, first of all, here it's better if we identify the dependence from Qi. Okay, let me identify the dependence here because it's extremely important. Because the probability density refers to a given value of the river flow. And it's clear if you look at the right-hand side, but let's make clear also in the left-hand side. Okay? When you look at an equation, basically, you have to find the same variable in both sides, unless you make some assumption that you have to make clear to specify. So when looking at this equation before than now, there was, the same. There was not an equality in terms of unknowns, which is not correct. So let me now compute the probability between 0 and Qi of P, and I have to call it now tau in the tau, because this is the variable which is integrated, integrating variable, I don't know how to say in English. And what is this? This is called, first of all, it's called capital PQI. Unfortunately, here there is a little inconsistency in the symbology, because this capital P is different with respect to this one. And I already told you that this one was not correct, okay? This one that I wrote here was not correct. And therefore, you don't have to get an interpretation of this capital P as the probability of getting QI, because it wouldn't be correct. So I should better use a new symbol, but I don't want to use a new symbol, because I think it would be more complicated. But this is not the probability of getting QI, because it would be 0, okay? We already know that the probability of getting QI would be 0. So what is this capital P now? This is the integral of the probability density from 0 to Qi. And what does it represent? Let me write it down. It's the probability of not exceedance of Qi. Is the probability of not exceedance. And try to think to it. And think at the fact that here you are multiplying the probability density of each river flow value for an infinitesimal increment of river flow. So basically what you are doing, you are starting from 0, from river flow equal to 0, and then you get increasing river flows. For each value of the river flow, you get the probability density, namely the probability of the river flow to fall within an infinitesimal range around it, multiplied by the infinitesimal range. So you are summing the probabilities of getting each value of the river flow. This probability, you may say, they are 0. No, they are not 0. They are very close to 0, but they are not 0. And therefore, you are summing the probability of getting river flow equal to 0 plus the probability of getting river flow equal to 1, to 2, to 3, for any number, any real number in this range between 0 and Qi. What are you excluding? You are only excluding the river flow that are greater than Qi. So basically, the sum that you get through this integral is the probability of getting any river flow up to Qi. It's the probability of not exceedance. This is very practical. Think about it. And this is very useful for us, because first of all, it's a way to assign a probability to a real variable. And it's something that is much interesting in hydrology. The probability of not exceedance is very interesting, because even if we are interested in extremes, like droughts and floods, probability of not exceedance is really interesting. So basically, if I design a dam for a river flow of 1,000, I want to know the probability of not exceedance of this river flow. Because if the river flow is exceeded, then it means that the dam may fail. So if the probability of not exceedance is 0.99, it means that I have only 0.01 probability to exceed the river flow, which is fine, because it's 1 over 100 chance of getting a dam failure. Okay, that's fine. It's very useful. And now, let me ask you this question. Do you think that these probabilities estimated in this way, and what I mean is, when I say these probabilities, I mean the infinitesimal probability of getting each real number. Because so far I said the probability is 0. No, it's not 0. It's very close to 0, but indeed it's very, very small. Okay? And these probabilities estimated in this way, do they satisfy the axioms of Kolmogorov? First and second axiom, yes, they are satisfied. These infinitesimal probabilities, they are greater than 0, or in any case they are not negative, so satisfy the first axiom, and they are lower than 1. So the first two axioms are satisfied. The third axiom, additivity, it's satisfied. Yes, look at here. If you integrate these probabilities, these infinitesimal probabilities over the whole range of river flow, you get 1, for sure. So the additive property is fine, works. So these infinitesimal probabilities that I defined in this way, through the definition of probability density, they are fine. The definition meets the axioms. So through the introduction of a new concept, the probability density, now I am able to provide a meaning to the probability of getting whatever real number is very close to 0. And it's not 0, just make an experiment. You could make an experiment with R. Take a river flow series and estimate these big probabilities for big ranges, and then reduce the range. Of course, you can't reduce much because it depends on the length of your series, but if you reduce it, you will see that you converge to a number that is very close to 0, but it's not 0. Of course, you can't reduce until a very small range because then you don't have enough numbers. But you will see that if you reduce it to a reasonable extent, you converge to an estimate. And then this estimate of probability density, this new definition of probability density is very useful because it allows me to define the infinitesimal probability of getting this precise value, real number of river flow,